Alright, welcome to part 2 of our Inflections and Shape videos. So what we're going to do is we've got a graph of f equals y equals f of x, and that's this function here. What this function is with numbers and squares and cubes and everything else is, I'm not 100% sure. But what we can do by looking at some of the defining points of this function, we can actually sketch what our derivative and our second derivative might look like. So we've got some points in here that we're going to look at and see if we can't work out what our first and second derivative graphs look like. So let's first of all have a talk through this, which will explain some of the process that goes on for this. So, for example, a turning point of our function f of x corresponds to a 0 of our second derivative. So our second derivative, when that's equal to 0, the slope of our initial function has to equal 0. So that's when you might see a point where it's completely flat. So it might be somewhere, maybe in this area, might be in this area as well. So keep those points in mind. An inflection point of our function corresponds to a stationary point of our first derivative and a 0 of our second derivative. So if we find a point in here that looks like an inflection point, what we're going to see is a stationary point of our first derivative and a 0 of our second derivative. If our function is increasing, then our first derivative is positive, and vice versa. If it's decreasing, then our first derivative will be negative. If our function is concave up, then our first derivative is increasing, and our second derivative is positive, and vice versa. If it's concave down, our first derivative is going to be decreasing, and our second derivative is going to be negative. It's worth noting that we're now talking about what's happening as we travel from left to right, or around a certain point of what our first derivative is doing. It's not whether it's negative or positive, it's what it's doing. Say if we go from x is equal to 0 to x equals 1. If we find that our slope, or our second derivative, first derivative, sorry, here is equal to 1, but over here somewhere it's equal to 3, well, it's clearly increasing between those 2 points. If we found that it was somewhere up here and it was going down like that, then our first derivative is decreasing. And what we'd find for our second derivative is that it would be negative. So let's look first. I do have a nice yellow colour to start with to mark down some points on what might be going on, or where might some of those critical points be. So let's have a look. It looks like we've got a local minimum somewhere around here. So let's put a point here, and we'll call this one our local min. Somewhere along here, it seems like we've got an inflection point. So what the inflection point is going to look like is where our function, the slope of it goes from increasing to decreasing, or vice versa. So from here, it looks like it's increasing, then around about here somewhere, looks like the slope's now decreasing. So let's put one in about here. So is this going to be a stationary point or a non-stationary point? So if it's a non-stationary inflection point, the tangent to the function here is not going to be horizontal. If it's a stationary point, the tangent is going to be horizontal. So much like here, at this point here, the tangent is horizontal at our local minimum. Is the tangent to this function here horizontal? No, it's not. So what we've got here is a non-stationary inflection point. Non-stationary inflection. Alright, it seems though we might have another one over here somewhere. I'm going to say it's about there. And the reason for that, it's about, this seems to level off, so it looks like the slope is decreasing at this function, and then after this point it seems like it's starting to increase again. So what is the slope of the tangent to this point? Well, to me it looks horizontal. So we can call this point a stationary inflection. Alright, so we know that there's going to be 3 points that we're going to use for our first and second derivative. So let's pick another colour, and for this one I'm going to use green, and that's going to be our first derivative. If it actually changes to green, bear with me. Alright, f-x is going to be this delightful green colour. So what is it doing around this local minimum point? Well, if we think back to when we're talking about what the sign diagram of what our first derivative is doing round a local minimum point, we know that it's going to be negative and positive for a local minimum. So let's do a scribble up here. So for a local minimum, which looks something like that, our sign diagram of f-x, we have our point here, x, is going to be negative, positive. So we know that it's going to go from negative to positive, and it's a local minimum, which means a tangent line in here is going to be, our slope is going to be equal to 0, so it's going to pass through the origin right here. We also know that it's going to do something with the x-axis here. Whether it crosses it or touches it, we'll have a look in a moment. But first, let's deal with our non-stationary inflection. So, our non-stationary inflection means that the slope is going from increasing to now decreasing, so it's going to look a little bit like this. So it's increasing, now it's decreasing, and over here it's decreasing and then increasing again. So it's not changing from negative to positive for our slopes here, but what we've got is when it gets to this point here, is that it's going to touch the x-axis and then increase again. And that's what our first derivative is going to look like. What our second derivative is going to look like, and let's pick another colour. Let's pick purple. Our second derivative is going to do something a bit different. We know that for when we have our slope here passing through 0, we're going from negative to positive. Our second derivative must be greater than 0. So it's going to start somewhere up here. So our slope, or if we think of it like this, if our derivative's slope is increasing, then our second derivative must be greater than 0, and vice versa. If our our derivative is decreasing, then our second derivative is going to be less than 0. So we can see that here it's increasing, 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 it's decreasing, and then it's increasing again. So it's going to start off positive, go through the x-axis here, and then increase at the other side. So it's going to look something like this. Now, it's not the best and straightest drawing in the world, but it will do. So it's also worth noting that at the stationary inflection point, the graphs of our derivative and our second derivative are equal to 0. So they're both passing through this point here. At a non-stationary point, our derivative is 0, our second derivative is equal to 0, and our first derivative is greater than 0. So if we have a look here again, our first derivative is increasing, it's going up, means that if our first derivative is going up, our second derivative is going down, and vice versa. So as this is increasing, our second derivative is going to be greater than 0. It's here, it's decreasing, so our second derivative is going to be less than 0. Once it gets to this point here, it starts to increase again, so our second derivative is going to be greater than 0. I hope this makes sense to you guys, and I want, if you got any questions, again, like normal, ask. Once you give a few of the exercises a go, it might start to become a little bit clearer on how we go about it. And as always, if you've got any questions, come and see me, and again, thank you for watching.